Here you see defined three vectors, each in 3 dimensions using IJK notation. The goal is to show that the dot product distributes over addition. Probably the easiest way to do this is to break the vectors into their constituent components and then perform the dot product. So what we want to do is first add the vectors w and x, and our strategy will be to develop this vector in the parentheses and then take the dot product with v, and then later reorganize terms and show that it's equivalent to the right-hand side of the formula. Vectors add by components, and so we have wx plus x sub x. So the x components, and I'll give the unit vector I, plus wy, and then x, y components, like that. And then finally the z components. So the sum of the vectors is straightforward. It's adding the components. Now we have 3 scalars multiplied by 3 unit vectors. So this is a vector. And so when you add 2 vectors, you get a vector. And so we can take the dot product of this new vector with v. And so I'll use this ellipses notation quite often, where I'm referring to what's inside the parentheses with just dot dot dot. So v dot anything in the parentheses, which is really this long vector here, is going to be vx times the first scalar wx plus xx. So that would have been the I components. There are no cross terms because the dot product only lines up the i's with the i's and the j's with the j's, etc. So this is going to be a scalar. Taking the dot product of 2 vectors gives you a scalar. And our second part of that scalar, which is the sum of 3 terms, will be wy plus xy times vy, and then vz times wz plus xz. Now, these 3 terms would constitute the answer if you just wanted the dot product, but the goal is to show that it's somehow equal to the dot product of v and w and then plus v and x. So it's going to behoove us to separate all the vw terms and all the vx terms. And one thing we're going to use is that scalar multiplication. So scalar multiplication is distributive. It distributes over scalar addition. And so we're fine. We can just reorganize these 3 terms into 6 terms. So this will be vx wx plus vx x sub x plus vy wy plus vy xy plus vz wz plus vz xz. So we have 4 terms on top, and another 2 makes 6 terms, so we have the right number of terms. And now we need to collect all the vw terms and all the vx terms together, so let's do that. Here's a vw term, so that's vxwx, plus, let's look for another vw term. No, here's one, vywy. That's not what we're looking for. Here's the final one, vzwz. Okay, so now let's look for all the vx terms, so it should be all the remaining terms, so vxxx, vxx sub x, plus Vy x y plus Vz x z. Now notice that the first three terms are equivalent to v dot w. Why? Because you see the x components in v and w multiplied, summed with the y components in v and w, summed with the z components in v and w, which is equal to v dot w. Similarly, with v and x, now this whole thing is a scalar. This is 6 scalars summed together, so you get a scalar. But the dot product is also a scalar. It looks like a vector because it contains vectors, but anytime you dot a vector with another vector, that's a scalar. And so we have v dot x is our second term, so this is a scalar and another scalar. And so we've proved that vector multiplication in the form of the dot product distributes over vector addition.